Well, let's do another exam. Here we have a Calc 1 exam, also known as Math 165, and it's exam 2. Now, exam 2 is a lovely exam. We've gone past our basics, and we're starting to get a little bit deeper into tools of differentiation, techniques, and applications. So it's a wonderful time. In this one, we're going to have 7 problems, so we're going to have a lot of fun doing it. Now, of course, with every exam, the first thing we should always do is put our name on it. So we make sure to give ourselves the credit because, well, we deserve the credit for all the work we put into it. So here we go. We're going to write the answers, right? That's what we want. We don't want the questions. We want the answers. So let's begin. Number 1. Let f of x equal square root of x. Find the linearization of f of x equals the square root of x at x equals 16. Now, there's a big clue on what we should do here. We see the word line. And of course, whenever we think of line in calculus, particularly in calculus 1, we think tangent line. It's almost like we go back and we start thinking of Bouchier. When you say tangent, you say line, tangent, line, right? Yeah. Okay, so anyways, the linearization is nothing to be nervous about. It's just really saying, hey, find a good tangent line, because the moral is the tangent line, it's doing a good job of behaving like the function. That's why we care about it. Okay, so what do we need? Well, we need to know a couple of things. We have our function, and that can help us get a point, but we need the slope. And the slope comes from the derivative. So find f prime of x. Well, square root of x, we can write that in a more calculus-friendly way. By calculus-friendly, more in line with our rules. So this is x to the 1/2. So f prime of x is 1/2, x to the minus a half. And if you want to convert back to more algebraic, well, that's 1 over 2 square root of x. All right, so we plug in 16. F of 16. Well, square root of 16, that's 4. F prime of 16. Well, that's 1 over 2 times square root of 16, so that's 1 over 8. Okay, now, what's the formula? Well, what's the formula for the tangent line? The formula for the tangent line, well, it's y equals f at a plus f prime of a times x minus a. Now, this is not the function. It's the function evaluated at the point. So don't plug in functions here, plug in numbers. Now, in our case, we say, okay, the function at 16 is 4 plus f prime of a, 1/8, and then we have x minus a. Now, a is that point right here. So this is our a. And we have a line. That's a linearization. And so there we go. See, that wasn't so bad. It's not scary at all. On to part B. Use the linearization from part A to estimate square root of 15. So what's the punchline here? So going back to what is the linearization? Well, the linearization is approximately the function. So we can say, hey, the function f of x behaves like 4 plus 1/8 x minus 16 for x near 16. Now we can say 15, we can say sure that's near 16, why not? And what is our function? Well, it says right here, square root of x. So we say, all right, square root of x, which is f of x, is approximately near that. So we can say, oh, so square root of 15 is approximately 4 plus 1/8 times 15, 15 minus 16. And 15 minus 16 is minus 1. So that's 4 minus 1 over 8. Now, if you write 4 as 32 over 8, subtract 1 over 8, you see, aha, that tells us that the square root of 15 is about 31 over 8. Now, it's not exactly that, but we're not after the answer to what is the square root of 15. We're after the answer to what's an estimate for the square root of 15. And there we go. We have an estimate. Life is good. So now we're ready. We know that when we see linearization, we're going to think tangent line and linearizations are about doing good approximations to the function near our point. No worries, we're definitely going to nail that kind of problem on any future test that we encounter. Number 2. Let g of x equal arctangent of x squared minus natural log of 1 plus x to the fourth. And of course, I read a problem like this and say, is it my birthday? Did my birthday come early this year? I see an arctangent. Ah, whew, I love arctangent. But okay, let's not get too excited, right? We have the rest of the problems to read. Find the equation of the line tangent to yg equals g of x at x equals 1. And then there's some simplify your answer and evaluate any term involving an inverse trigonometric function. So, all right, so really this one's not so bad. In fact, it's a little bit more straightforward, right? Because it's saying, hey, what are we looking for? We're looking for the line tangent, or if you like, the tangent line. So you say, well, we know how to find tangent lines. We were just doing that a few minutes ago. So in particular, we say, all right, we have y is equal to, in this case, the function is g of a plus g prime of a times x minus a. That's the tangent line. We just have to start filling in our various pieces. Now we have a few things. We know that a is equal to 1. You might say, well, how do we know that? Well, because it tells us where our tangent is happening. We have our g of x, which is arctangent of x squared, and minus the natural log of 1 plus x to the fourth. Oops, that's very sloppy there, but we all know what we mean. We're among friends here. We know what that means. Now you might say, why is it on this test? Well, because arctangent and log are both things that we've recently acquired. So in some sense, we're really testing on do we know how to take derivatives of arctangents and logs. All right, so let's do that. G prime of x. Well, the derivative of arctangent, the rule is 1 over 1 plus whatever you put inside squared. So in our case, the inside is x squared. So it's x squared squared. Right? Now, are we done? No. What do we need? Chain rule. So chain rule says it's 1 over 1 plus the inside squared times the derivative of the inside, which in our case is 2x, minus. Now, derivatives of natural logs are great. They're really fun. Here's what you do. You put a fraction, and you say, all right, whatever's on the inside of the log goes downstairs, 1 plus x to the fourth. And then take the derivative, and that goes upstairs, 4x cubed. And you're done. That's it. That's the whole derivative. And, well, that's pretty clean. So, again, it's chain rule, right? So the derivative of natural log is 1 over. So we have 1 over the inside times the derivative of the inside. Now, if you stare at this for a second, you'll notice they both have 1 plus x to the fourth. So we could, if we wanted to, say they both have the common denominator of 1 plus x to the fourth. So this becomes 2x minus 4x cubed. Divide that by 1 plus x to the fourth. Now, we don't need to do this step, but we could. What do we need to do? What we do need to do is plug in 1, because we need g of 1 and g prime of 1. So what is g of 1? Well, that's arctangent of 1 squared, which is 1. And then we have minus the natural log of 1 plus 1, which is 2. Now, natural log of 2, there's not much you can do with that. But we do remember the instructions, because, you know, we remember instructions. It says, no term involving inverse trigonometric function. Okay, so we got to somehow say, what is arctangent of 1? Well, that's pretty simple, actually. It's a really nice value for arctangent. So you can think of this as saying tangent of which angle is 1. And the angle where tangent of theta equals 1 is pi over 4. So pi over 4 minus log 2. That's our g of 1. And now g prime of 1. So g prime of 1 is equal to what? Well, you plug in 1. The nice thing is plugging in 1 into polynomials is pretty easy. So it's going to be 2 minus 4 over 1 plus 1. Well, that's minus 2 upstairs, 2 downstairs. So you end up with a minus 1. So what's our final line? Well, now we just plug in what we know, because we know things. What do we know? Well, we know y is equal to g of 1, so that's pi over 4 minus natural log 2, plus g prime of 1, which is a minus 1, so we can write it as a minus, and then x minus a, so that's x minus 1. And if we wanted to, we can rearrange this. So we could say y equals minus x, and then we could have a plus 1 plus a pi over 4 and a minus natural log 2. And there we go, our tangent line. And I know this looks really complicated, but you start and say, oh, it's just a number. And then it's a really weirdly written number, but a number nonetheless. And so life is good. 2 problems down. We're doing great. Number 3. Use logarithmic differentiation to compute the derivative of the following function. And we have e to the minus 1 over x squared secant of x to the power of x. Oh, terrible. Why? Well, notice we have a secant x down and an x up. So we have to use logarithmic differentiation. It's unavoidable. Any way that we have to actually take this ultimately at the end is a flavor of logarithmic differentiation. And it says here, your final answer should be expressed completely in terms of x. Now, that's just saying, why do they have that note there? Let me just explain why that note is there. One of the ways that people will do a logarithmic differentiation problem is they'll say, well, log of y equals log of the function we're trying to take the derivative of, and then take the derivatives, you end up with 1 over y prime, chain rule, with the natural log of y, equals stuff over here. And so sometimes people write as y prime equals y times the original expression. But that y, that's what they want to not have. So when they say all in terms of x, they don't want that. Well, that's easy, because y is the original function. So you have y prime equals the original function times stuff. Now, more precisely, this is the formula I like to use, and it's a personal favorite of mine when it comes to logarithmic differentiation, because I feel it's a better formula. So it says the following. If I want to take the derivative of f of x, that's the same as f of x times the derivative of the natural log of f of x. So that's the idea. Now, why do all of this? Well, because natural log has some magical, wonderful properties. It's a great function. It's the kind of function that we'd probably want to hang out with on a weekend, because it does some really cool things. So, for example, products become addition, and division becomes subtraction, and exponents can come down. These are all fantastic properties that the log has that helps us rewrite this expression. So essentially, the key here is that if you have a bunch of stuff sort of like mushed together, they say, I really want to pull it apart. And when I say mushing, I'm the kind of multiplying mushing. So lots of multiplication crammed in. You say, take log, pull it apart, and then what you'll have, the individual pieces are going to be something that's easier to digest. Okay, so now we have our game plan. All right, so here we go. We're going to compute that derivative. So we have y prime. According to our rule, it's the original function. So we just write the original function over again. Minus 1 over x squared secant of x to the x power. Then we're going to times that by the derivative of the natural log of, same thing, e to the minus 1 over x squared, secant of x to the x power. And, okay, you have to make sure you count your parentheses, but yeah, okay, we got the right number of parentheses. All right, so before we take any derivatives here, pull in their powers of logs, pull things apart, separate. And so when you do that, you'll have e to the minus 1 over x squared, secant of x to the x, and I know that this is one part of the process that makes it like, it feels like you write a lot, but you have to keep it going. Times the derivative, we haven't done any derivatives yet, and now we say, okay, I have a product here, so then I can separate them into two pieces, and here I have natural log of e to the minus 1 over x squared, so that becomes minus 1 over x squared. We can write that as minus x to the minus 2. Okay? And then plus, now, right, because it's natural log of a, that's that part. And then we're going to do natural log of b. And again, we see a power, so we can put that all the way down. So that'll become x natural log of secant of x. And there we go. Good. So what happens next? Well, we have e minus 1 over x squared, secant of x to the power x, and we haven't taken any derivatives yet. So you might say, we're done. No, we haven't done any derivatives, so we can't be done. But we're almost done because we're ready. So taking derivative here, what do we have? Well, the minus 2 comes down, so that'll give us 2. Then we're going to have x to the power minus 3, right? Because bring the power down, subtract 1. Now here, product rule. Derivative of the first is 1 times the second, so that'll be log secant of x, plus the first, which is x, times the derivative of log secant. Well, okay, so if there's a log, you put a fraction. The original function goes downstairs. And now, take the derivative of that, put it upstairs. So derivative of secant is secant tangent. And we say, okay, well, we can do one more simplification. We're here, why not? We see that the secants can cancel. And so we end up with the following expression. E to the minus 1 over x squared, secant of x to the x power, and we can write this as 2 over x cubed if we want to, because why not? That's what x to the minus 3 means, plus natural log of secant, plus x tangent x. And there we go. That's it. That's the answer. We did it. Wonderful. So logarithmic differentiation, a wonderful tool. Oftentimes we'll tell you explicitly, here's what you do. But even if they hadn't told us, we could have known, right? Because we see a function to a function. Function to a function, logarithmic differentiation has to come into play in some way, shape, or form. And so, well, all right, wonderful. We're just running. We're almost halfway through. Almost. This brings us to problem number 4. A light located at the origin shines at a wall located at x equals 50 feet. A person 5 feet tall casts a shadow h feet high on the wall. See the diagram. So we have the light. There's our wall. You can tell it's a wall because it has the word wall. There's our 5 foot tall person. You might say, well, that's a very convenient height for a story problem. Well, you know, don't tell anybody. My wife is 5 feet tall, so she makes a wonderful candidate for story problems. It's not the only reason I married her. It's a bonus, though. But okay, anyways, all right, so there we go. There's our picture. Now, if the person is currently 10 feet from the light and walking towards it, okay, so here we have, this is 10 feet and moving in. So, walking towards a rate of 1 foot per second, find the rate at which the height of the shadow is changing. All right, let's do a little thought experiment first. If I am a person, because I am, turns out, true story, I am a person, and I move closer to the light, what's happening to my shadow? It goes up. It moves higher. So we know our final answer better be a positive number for the rate at which the height is changing. And if it's not, whoops, go back and check our work. Okay, so now what do we need? Well, we need to introduce some various variables. So let's think about what we could call things. Well, I like to call things x. X is a wonderful variable. So suppose we do call this x here. So the distance person is from the light. And then what do we have? Well, we actually have two triangles. We have the small triangle here and the big triangle there, right? And what's true about these two triangles? Is there anything that you can say? Are they similar? Yes, 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 yes. Okay. Ha ha ha. Yes, we see it. They are, in fact, up to scale the same triangle. And so we say, okay, well, that's good news for us. So we say, aha, this is similar triangles. And by the way, we haven't said it yet. What kind of problem is this? And the answer is it's related rates. How do we know it's related rates? Because we're told information about one rate, which is how quickly this person's moving towards the light. And we're asked to find information about another rate. So we're asked to find some relationship between two rates, and hence related rates. All right, good. No big surprises. All right, so if we think about these triangles, well, we're not going to use what we'd call the hypotenuse, but we can look at the ratios. So this distance here is x. We can say x is to 5, so the horizontal to the vertical is the same as this horizontal. 50 is to that vertical, h. Or we could say, x times h has to equal 250. All right, so what do we know? Well, we have a couple of things that we do know. So let's mark down what we have. The following. Okay, the person is currently 10 feet away. Okay, so we know we care about at x equals 10. Now, by the way, if we know x equals 10, what's h? 10h equals 250. That says h has to equal 25. So x equals 10, h equals 25, and we also have a rate of change, dx dt. Now, it's moving towards it at a rate of 1 foot per second. So what do we put here? You see me leaning in. You're like, Steve is anticipating that I'm going to say 1, and he's going to go like, is it? Okay, so the answer is it's not 1, but it's almost 1. It's minus 1. Now, why minus 1? Well, you see, when we talk about derivatives, it has direction. In other words, the sign means something. And so we're walking towards the light, so that distance is getting shorter. So it should have negative value for the rate of change. All right, good. So we're almost there. We have all our pieces in place. And, well, let's see what we do. We have our relationship, so we take a derivative. And so we take the derivative of both sides with respect to t. So what do we have? Well, we'll have derivative of the first times the second plus the first times the derivative of the second. All right, and that's going to equal the derivative of this side, which is 0. Now, plug in what we know. We know dx dt is minus 1. We know h is 25. We know x is 10. And dh dt we don't know, but that's okay. We're trying to find it. If we already knew it, it wouldn't be an exciting problem. So we have 10 dh dt is equal to 25, because we can move that across, or dh dt is equal to 25 divided by 10. Of course, we could first divide out of 5, which is the same as 5 divided by 2, or 2.5. If we wanted to add units, well, h is being measured in feet, t is being measured in seconds, because we see it over here. And so we could say it's 5/2 feet per second. In this case, it didn't ask us for units. Sometimes it does, sometimes it doesn't. But the nice thing about derivatives are units are what you expect them to be. No surprises. Isn't it great? Don't you wish all your classes were like that? No surprises at all. And so there we go. Our beautiful rate of change. We have found the rate at which the height of the shadow is changing. It's changing at 5/2 feet per second. Remember our thought experiment at the start? We said it should be going up, should be positive, and it was. If we hadn't put that minus in, it would say minus 5/2 feet per second, and that would leave us saying like, what? How is it getting smaller? So that's sort of a clue. Make sure things make sense. Because, you know, common sense is a really amazing tool to say, oh, maybe I made a mistake, or maybe I didn't. And so it's all right to think about things and say, is this reasonable? Is this good? Could it even be correct? Oh, of course it is. Come on, we're great. We're really, really good. All right, well, let's keep going. Number 5, let f of x equal x squared minus 3 times e to the x. And we have a bunch of things to do, so let's just start at the beginning. It's a very good place to start. So find all x values that are critical points of f. So those are places where the derivative is undefined. I like to include boundary. Our derivative is 0. But these are pretty nice functions. And so we only really need to worry about the derivative is 0. So we're going to take our derivative. And so, all right, product rule, because we have x squared minus 3 times e to the x, two functions multiplying together. And so we say, all right, f prime of x is the derivative of the first, 2x, times the second, plus the first, x squared minus 3, times the derivative of the second. And the derivative of e to the x is e to the x. Sometimes it makes you feel like, wait, did we really take a derivative there? Yes, we did. It just so happens it looks very much like what we started with. All right, well, let's clean this up. Well, one thing we can do is pull out the e to the x, and we'll put that on the end. And then we say, well, we have the 2x and the x squared minus 3. We can rearrange that, put those in order. So x squared plus 2x minus 3, e to the x. All right, now, does this factor? If you have a nice calculus teacher, which of course all calculus teachers are nice, it's just inherent. They're very kind-hearted people. Then what we'll see is that this will factor. So can we think of two numbers that multiply together to give negative 3, but added together to give positive 2? Well, plus 3 and minus 1 are such numbers, right? And you can check. X squared minus x plus 3x is plus 2x and minus 3. All right, so again, this is very nice. Nowhere is it undefined. Everywhere is good. So the only critical points are when we have things equal to 0. E to the x can never be 0. So it's one of these two pieces which has to be 0. So that leads us to saying that we have critical points are at x equals negative 3 and positive 1. And that's part A, because all we need to do was find the x values that are critical points. Okay, cool. Well, that's great. Now we move on to part B. Determine the open intervals on which f is monotone and state whether f is increasing or decreasing on the intervals you found. So we want to say, are things going up or are things going down? Now, essentially, this right here, monotone, we're asked about increasing, decreasing. So whenever you hear things about monotone, you're saying, all right, increasing, decreasing, up or down. And so that comes back to the first derivative. Now, the nice thing is the first derivative, how can it change from positive to negative? And the reason I talk about positive and negative is the sign of the derivative tells you going up or going down. Positive derivative, we go up. Negative derivative, we go down. All right, so the derivative, that tells you everything you need to know about what going up or down. The only place we can change sign is at the critical points, which we've already found. So I like to draw a line. And then I put them down in order. There's 2 points, and it turns out -3 comes before 1. And now, let's look at the signs of the derivative on each interval. So, pick a number, say between -3 and 1. 0. Plug it in, and we can use this form of it here. We'll get positive, negative, positive. In fact, e to something will always be positive. So, we say, the derivative here is negative, right? Plus, minus, plus. How about pick something big, like 2, or 1,000,000, or 2. Whatever number, just anything bigger than 1. Positive, 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 the optimist range. So everything's positive, multiplied together. The derivative is positive. Something below -3, like -4. It doesn't have to be -4, it can be any value below -3, but -4 works. Negative, because -4 plus 3 is negative. Negative, positive. So altogether, the derivative is positive. So it says here we're going up, then down, then up again. All right, so we have increasing will be where? Well, up to -3. So we can write that as -infinity up to -3. And we're open intervals, and so we put the parentheses. You know, there's the square brackets, which is the closed. Parentheses means open. There's a wonderful discussion, which your calculus teachers will not agree on, about whether it should be open or closed. They should be closed, but that's a different story, and we're not going to get into it because I've already had enough arguments with calculus teachers. We're just going to say open. All right. And, okay, 1 to infinity. And we are decreasing from where? Well, from -3 to 1. And we put a box, because we now have identified our intervals on which we're monotone and which ones are increasing and decreasing. Okay, great. Well, now we're ready for part C. What does that ask? Use your works in part A and B to find all x values corresponding to local extrema. State if these values correspond to a local maxima or a local minima, and state the theorem you used or explain your answer. Now, I'll say explain my answer is I'm going to use by first derivative test. I'm not very good at long explanations. So the theorem here, or the idea, is the first derivative test. So what are we looking for? Well, we're looking for local extrema, classifying critical points. So we look at -3 and 1, they are our critical points. Nowhere else do we have critical points, so nowhere else can we have local extrema. So we see that -3 is what? We're going up, going down. So what does that look like? It looks like -3 is at the top of a hill. So that's a local maximum. Now what about 1? Well, we're going down and going up. Down and up. So 1 is at the bottom. It's in a little gully, if you will. So 1 is a local minimum. And there we go. First derivative test. That's what we're using. That's our idea. And of course we could use second derivative test, but that sounds like work. We'd have to compute another derivative. Ugh, I don't want to do that. Why do that when we already have the work in part B? And so there we go. We have our answer. Wonderful. Number 6. A rectangle has its base on the x-axis and its upper two vertices on the parabola y equals 24 minus 2x squared. What is the largest area the rectangle can have? And what are its dimensions? So, well, they gave us a picture here. And so we have this rectangle, and we're trying to optimize it so that we have the largest area. And we think about it and say, okay, how does one go about finding area? Well, generally speaking, for a rectangle, what we would do is we would take the height times the base, right? Or length times width, whatever you want to think of it. So if we think about a point here, we can think of it as this is at the point x, comma, 24 minus 2x squared. So I'm just going to move this corner around, and it could fall anywhere on the parabola. Well, not quite anywhere. We have some certain conditions. For example, we're going to assume that x goes from 0 all the way to, well, this would be square root of 12. So there's a sort of underlying 0 less than or equal to x less than or equal to the square root of 12 assumption. And we'll talk about that in a moment, but for now, let's go in and see what's going on here. So what's the area? So the area is we multiply, right? 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 Oh, Steve, you're trying to make me question whether I know things. I know things. So this turns out it's almost the area. You have to be a little bit careful. If you just did x, that's only half the base. So we just say, okay, double, and that's our real area. So 2x times 24 minus 2x squared. Now, in terms of the optimization, it doesn't change anything. In terms of the final answer, well, it'll be off by a factor of 2. So our area for any choice of x is 48x minus 4 times x cubed. So think of this, we'll call this a of x. And we're trying to optimize it. Now, how do we know we're trying to optimize? What is the clue that this is an optimization problem? Well, you notice there's an est. Whenever you see an est, you know you're trying to do some kind of optimization. Okay, so we now take our derivative. So a prime of x would be 48 minus 12x squared. And we set this equal to 0. Well, all right, solving. You can add 12x squared and divide by 12. You get x squared has to equal 4. And so x equals 2. Now you might say, whoa, Steve, plus minus, plus minus. Remember, we talked about x can only go between 0 and square root of 12. So it can't be the negative. Okay, so x equals 2. It also says you can't have a negative length. You know, that's why we throw out the negative 2. All right, now we're basically done. What do we do with this? We do a couple of things. We're after the largest. Now, our claim is that it's 2. You might say, are you sure about that? Let's go ahead and just check. So you might say, maybe it's at 0 or square root of 12. There's reasons to think not. But one of the things we can do is check the second derivative. So a double prime of x would be 0 minus 24x. And so a double prime of 2 is negative 48, which is less than 0. So that tells us that indeed we are at a local max. So that is a good sign. We also know that it tells us it has to be the max, because 2, we're at a high point, and then it goes down in both directions. So in particular, by the time we hit 0 and this wonderful value square root of 12, we're lower than where we were at before. In fact, 0 would be a really crazy rectangle. It would have no width. Square root of 12 would be a different crazy rectangle. It would have no height. So at the endpoints, our area is 0. So it's definitely not the endpoints where we're doing our largest. Smallest, yeah, they're both candidates for that. Okay, so that was work we didn't need to do. But keep in mind, sometimes they do ask for justify why this is in fact the largest. And so maybe don't forget about how to do that. So it's okay for us to take a little detour. All right, so what do we need? Well, what's the largest area? Well, when x equals 2, we have our dimension, so this is our width, and this is our height. And so our area, well, all right, let's do our dimensions first. We'll go ahead and just get that out of the way. We're going to have x equals 2, so it'll be a 4 by, and then 24 minus 8, 16. Okay, and so the area, maximal area, would be 4 times 16, which is 64. And there we go. That's our lovely answer. A lovely, lovely answer. And all right, well, we found the largest area, and we found its dimensions, and so we're done. Life is good. And all right, 4 by 16. Oh, well, you know, it's the picture might make you think, really? But if you look at this point right here, that's the square root of 12. Square root of 12 is like 3 point something. So 2 would be kind of roughly here. So that's roughly what it looks like. You're like, oh, okay, I could see that. I could see that. And the picture's not to scale. Don't tell anybody I said that. It's very misleading sometimes. Sometimes you're like, this picture is wrong. It's not to scale. But that's all right. We don't need it to be. We have the math. And so we're good. We're better than good. We're great. Our final problem. Well, I guess all good things must come to an end sooner or later. So number 7. The first derivative of a function f of x is given by f prime of x equals x minus 2 quantity squared times 3x plus 1. All right, so for part A, find the x-coordinates of the critical points of f of x and determine the intervals on which f of x is increasing and decreasing. So for critical points, we say, is there anywhere where it's undefined? Nope. Any boundary? Nope. Zeros? Oh yeah, we got those. Okay, so when we set f prime equal to 0, well, that tells us that we need x minus 2 quantity squared times 3x plus 1 equals 0. And, well, it's already factored for us. So it tells us we have 2 candidates, namely at 2 and negative 1/3. All right, so those are our critical points. All right, so that's part of our answer, so we should box that. And then there's a little bit more for part A. Determine on the intervals in which it's increasing, decreasing. So for that, we're switching gears a little bit, so we'll change colors, right? Different ideas, different colors. And I like to draw the line. I mark my points. Negative 1/3 comes before 2. And I plug in numbers. So for example, I can plug in 0. And when we plug in 0, we have a positive times 1. Oh, okay, so f prime here is positive. Plug in a number like 4, we get a positive times a positive. Oh, okay, so f prime here is still positive. And then negative 1/3, well, plug in like negative 1. And this is positive. right? Because you're squaring it. Well, now that's negative. So the derivative is negative. So what's happening? Well, we're going down until we hit negative 1/3. Then we're going up and up again. So, of course, because the derivative is 0, we kind of like level off and then go back up. But we say, okay, we are decreasing. We'll start with that one because that's a little bit easier. From minus infinity all the way down to minus 1/3. And okay, we'll say open interval. All right, so there's a big argument, open interval, closed interval, but all right. And we're increasing, always going up from negative 1/3 to infinity. That's, I would say, is true, right? And I say, well, what about 2? Aren't I not increasing at a point? Well, the problem is you can't talk about increasing or decreasing at a point because increasing is about comparisons. I can't compare 2 to itself. I can compare 2 to other points. And as soon as I compare 2 to other points nearby, I see, yeah, I'm always going up. So that's why it should be including 2. But, all right, that's my opinion. So there we go. All right, so on to part B. We've run out of space for part A, so hopefully we've run out of question as well. Find the x-coordinates of the inflection points of f of x and determine the intervals on which f of x is concave up and concave down. Okay, well, what do we need? Well, if we're talking about inflection points and concavity, we need the second derivative. So we have the first derivative, so let's find the second derivative, f double prime. Well, okay, so we can do product rule. So the derivative of the first, 2 times x minus 2 times the second, plus the first, x minus 2 squared, times the derivative of the second, which is 3. Now, we can factor out an x minus 2 because that's common. So this is x minus 2 times, in the first term we'll have 6x plus 2, because we have the 2 times 3x plus 1. In the second term, we have 1x minus 2 still left, times the 3, so that would be plus 3x minus 6. Okay, so that becomes x minus 2 times, we'll have 9x, and 2 minus 6 makes minus 4. Okay, so we're looking for when can we flip concavity. Again, where is it undefined? Boundary points, zeros. The only thing we have to worry about is the zeros. Set this equal to 0. Say, okay, our potentials. We don't know yet whether they are, but we kind of know. We'll talk about why we kind of know in a second. 2 and 4/9. Okay, so those are going to be our inflection points. Why do we kind of know those are inflection points? Well, the trick is to say, look at the powers. They're both to the first power. So these are single roots, which means that the function crosses through the axis. So it crosses. Whereas in a double root, as we had in part A, it bounces. And so it doesn't change the sign. So that's why we had this strange thing where the sign didn't change. But because we see that these are both to the first power, we see, aha, the second derivative will in fact change at both places. Ergo, they will both be inflection points. But we should still check. So let's do that. And let's see what's happening. All right, so we mark. We have 2 and 4/9. Well, 4/9 is smaller than 2. So we'll mark here and there. Say, all right, well, pick a value. I'll pick something bigger than 2, 3. 3 minus 2 is positive. 27 minus 4 is positive. So that says your second derivative is positive. So we are concave up. All right, between 4/9 and 2, well, we could pick 1. 1 minus 2 is negative. and 9 minus 4 is positive. So f double prime is negative, which means that we're concave down. And now, something below 4 ninths, like 0. 0 minus 2, negative. 0 minus 4, negative, which means negative times a negative is a positive. So we're concave up again. All right, so what do we say? Well, we are concave up from minus infinity up to 4 over 9, and from 2 up to infinity. And then we're concave down from 4 over 9 all the way to 2. And that's our answer for part B. Again, we've run out of space, so good news is we've run out of problem for part B. That leads us to part C. Okay, so we have at critical point x equals, well, we fill in from parts A and B, right? We have two answers, so we say, okay, at critical point, all right, now, we have to be careful here, because we say, at one of these critical points, f double prime is 0. Well, which one is it? Well, it's the 2, because it's the one that gets repeated. So x equals 2. We know f double prime equals 0. By the first derivative test, f must have, well, 2, see how it goes up, up? Neither a max nor a min. Good. So that must mean that negative 1/3 is the other one. That goes here. At negative 1/3, we're in this place. So f double prime is positive. And when f double prime is positive, that means that we have a minimum. Okay. Good. All right. Well, what's left? Are we done? No. We continue on the next page. Oh, just when you thought you were out, it pulls you back in. All right, that's okay. We're happy for that. We're happy to see that. And of course, we can see that it's going to be a minimum because we see down and up. So that's good that we see that. All right, so what's the next page? Well, this is a 2-page problem. So part D, using the fact that f of 0 equals 0, sketch the general shape of the graph of f of x. Now, it doesn't say sketch exactly what it is, it just says what's happening. So let's talk about the behavior. We know it's going uphill from negative 1/3 to 2. And so at 0, we've got to be going uphill. At negative 1/3, well, let's say, here's negative 1/3, I don't know. We have to bottom out. So we're going to have, we'll say we bottom out here. And so we're coming down, and we're going back up. All right, so there we go. We've marked our critical point at 0, coming down, going up. Now, what's the next interesting point? Well, there's actually an interesting point here at 4/9. And so 4/9 is about halfway, and so we'll put it, and that's going to be an inflection point. We'll get to that in a moment. And then after 4/9, there's the next interesting point after that is a 2. Okay, so let's say we're here at 2. And there the derivative is 0. So we're going up. Okay, so we're concave up, and now we're going to flip to concave down, and then we'll level off. Now, I don't know exactly what the value of 2 is. That's why we say general shape. And then we don't go down, we level off, but then we go back up again. And so our shape is, we come down, we turn around here at 1/3. We have an inflection point here at 4/9. And then, of course, we have an interesting point here at 2. So we have our min, our place where we level off, our inflection point there and there, concave up, concave down, concave up. So we have all of our pieces putting together what we had from these little stretches here. And all right, there we go. There's our answer for part D. Wow, what a problem. What a problem. I mean, such a problem, we couldn't even fit it on a single page. But that's all right. Our minds are open and we can just keep going for quite a while. But actually, not anymore, because that was the last problem. All right, well, I hope this is helpful. And I hope that if you're getting ready for a test, that you're going to go in there head held high and like, I can do this. Because you can. You can. This is not meant to be scary or meant to be only understood by a few. It's meant to be understood by you. All right. I hope you do great, and I hope to see you again. Bye.